about origami. Okay? How many of you have tried origami at some point in your life? Almost everybody. So what's the key to getting an origami structure the right way out? So how do I, in order to get a snake or a frog or a bird or a crane or something like that, you have to do two things. You have to be able to fold at the right place at the right time. Right? So the sequence of folds matters and in time, and the location of folds matters in time. So you can ask a question about, is it possible to do no-hands origami? Can you take your hands off and prescribe some physical law or mathematical equation which essentially does origami for you? It turns out, of course I wouldn't be here if that was not true, it turns out you can. Right? So the little device that I want to show you is this structure over here. It was invented, or at least it was thought to be invented. It was thought to be invented by a man named Kuro Miura. And what you can actually see, it's I can zoom out a little bit, if it's possible. Can't see the whole thing. Well, let me actually indicate it from here in front. So this object has got folds, and it's rather beautiful because if I pull it, the whole thing opens out, and the whole thing closes simultaneously. Okay? And that is a beautiful example of the foolishness of mankind. I say that because when you're driving a car, at least in the 20th century, when you're driving a car, you had maps in the car. Nowadays everybody has GPS devices. And you have maps in the car. How are maps folded? So every fold is perpendicular to every other fold. So therefore, it's easy to open out the map because it's only one way to go. You keep increasing its size. But on its way back, if I have n folds, each one has two possibilities, so I have two to the n possibilities. And of course, you know what that leads to. A tremendous amount of frustration. Okay? Now, let me tell you about the foolishness of mankind in designing maps. And the foolishness of mankind in designing maps is that the only way in which the folds would not work with each other, the only way when the folds would be decoupled, that means if I fold in this direction, it doesn't affect what's happening in that direction, is if the folds were perpendicular to each other. Anything else I do, if I make the folds at an angle to each other, like here, then the whole map will open at once and close. Nobody seemed to realize that until Miura did, and he patented it. And if you go to Tokyo now, you can buy maps of the Tokyo subway and of parts of Japan which are folded like this. Okay? Of course, nature, of which we are a small part, but only a small part, realized this 100 million years ago. Okay? So in spring, as is now the season, in fact, leaves, this is the hornbeam, but it's not limited to the hornbeam. You see this in other plants as well. And insect wings, if you look at a ladybird, and if you have the courage to essentially pluck the wing out, I'll be done in a couple of minutes. You actually see the same sort of pattern. And we are trying to understand how that pattern forms, and we run into an accident. So the accident is, if you just take a piece of Jell-O and you dry it, the pattern forms spontaneously. Okay? So there you see the pattern forming spontaneously in biology, but you might wonder whether there's a lot of genetic control, and here there is no genetic control. It's just a drying piece of Jell-O, and you see exactly the same pattern that you see on top. Okay? So again, this suggests that there's something simple. There's a pattern, there's a shape. How can we understand this? Well, it turns out that we use mathematics here. So this is in papiro, in paper, in vivo, in vitro, drying in gelatin or a glass-like substance, and that's on the computer. Exactly the same thing. Why does it form? Well, it forms because it turns out that the energy of the thin film which sits on this Jell-O is actually most easily minimized by forming these structures. So there's a very simple principle, and the principle is the minimization of energy that gives rise to these structures. Okay? And then it raises a whole bunch of questions. What are the properties of such a piece of material? So unlike most materials, which if I pull in one direction, shrink in the other direction, here if I pull in one direction, it expands. Okay? So it has an interesting property which the individual paper, the individual sheet of paper that it originally started out with, does not have. If I stretch paper, it either doesn't stretch at all, or even if it stretches a tiny bit, it will shrink in the direction. Here, by building in these creases, I pull in one direction and it expands in the other direction as well. So you can get all kinds of cool properties associated with this. So I think I'm out of time, so I was going to try and do another experiment, but
Can we have one more experiment?
Yeah, but it's actually sitting there in the back, because we needed to heat things up. I like this experiment. I'll tell you about it as I hope we'll get it in front. I like this because I have friends who tell me that nothing is more boring than watching paint dry or watching mud crack, and I would like to disagree. And here's why I'd like to disagree. These are, so I showed you Giant's Causeway earlier. Thank you. Hasn't really dried, has it? So I was trying to do an experiment for you, but it hasn't worked. So one experiment failed. It'll work by tomorrow morning. So I just basically took some cornstarch, and you can try this experiment at home. I took some cornstarch, mixed it with water, and let it dry. And the question that you're trying to understand is, when do cracks form? What sets their size? What sets their pattern? What sets their symmetry? That's on the global scale, unfortunately. That's in the lab. That's not cracking, it's wrinkling. These are two human beings over here. This is in Staffa, which is, I think, of the coast of Ireland, if I recall. You see these columnar joints. So these are very large cracks, and at some location the rock has fallen apart, fallen away, and so you can expose these columns. That's why they're called columnar joints. This is on a scale of tens of meters. Look at the scale bar over there. That's on the scale of millimeters. This is an experiment done by a collaborator and colleague of ours, Stephen Morris. Cornstarch. If I didn't show you the scale, the absolute scale, the shapes would be the same. Another example of where you actually, if I understand the phenomenon on one scale, I can extrapolate to another scale, because the physics is almost the same. I say almost the same because over there it's driven by drying, over here it's driven by cooling. And from a mathematical point of view, there is a very deep analogy between the equations if I replace the variable, which is temperature, associated with changing the stress here, with, turns out, the pressure, or equivalently the amount of water in the other problem. And they are completely analogous. If I replace one by the other, mathematically I see similarity, and physically I see similarity. Okay? So I'm sorry that experiment didn't work. I want to show you a movie of what the crack patterns essentially look like, because I was not sure the experiment would work. So these are crack patterns that you see, and what you're seeing is essentially a CT scan, a tomography, of how the cracks form as a function of depth. So as time progresses, you're looking deeper and deeper into the sample when that starch is essentially drying. And what do you see? You see the size of the cracks increase. So when you don't control the drying rate, when you just leave it out, as I've done over here, as you go deeper and deeper, the size of the crack increases. Makes a lot of sense, because to pull water out from very deep takes very long, and therefore it's very hard to essentially make small cracks. Okay? Was there a legend which said now that you switched to the controlled case? Let me see if I can. Okay, so that was the first experiment. Now they controlled the drying rate. So they kept increasing the power required. So they kept the rate of drying constant. And now what you see is that initially there is a change in the scale of the crack. Then it reaches a particular size right about now. And now the size doesn't change. The symmetry changes, but the size doesn't change. You see that? That's because you're pulling the liquid out at the same rate. Unlike in the previous case, when you're not pulling it out at the same rate, you're just keeping the temperature or the humidity outside constant. Okay? All right. So you can make a theory for this, and I want to connect this, as I promised, I want to connect this to other things. In fact,